We've already discussed there are 5 categories here of these shape producing processes. Casting, we've covered pretty exhaustively. We're going to move now on to uh, material removal, or we could also call this machining. This really spans chapters 20 through 26. The chapter 2021 kind of covers general content equations, solution processes, that sort of thing. And the individual processes are covered here in these chapters as shown. This is the most important of all the basic manufacturing processes, okay? So many of the other things that we do. Remember, we talked about casting, how often you'll cast your part and then you want to take it and do some grinding or machining or some other process there. And so now this is kind of a companion process for really all the other things that we've talked about, that we will talk about. Okay, there's 2 kind of different categories. There's the single point and then there's the multi-point. Okay, the difference, as you can probably guess, just is how many points or how many teeth or how many places does the tool impact or contact the workpiece. As we can see for turning on a lathe, fly cutting, this is something that happens on an end mill, or a boring operation, which also is on a lathe, that these are considered single point tools. Just one quick note. Notice here that this boring is essentially the reverse of the turning, right, or the lathe work. So both of these happen on a lathe, the turning and the boring. The turning happens on the outside. The boring is essentially just uh, interior turning. When we talk about multiple point or multi-point tools, we can see obviously sawing, that's a familiar one from lumber country here, but drilling, milling, broaching, and grinding. These are not all, but these are the ones that we're going to cover in some detail today. And this is where you've got, as we talked about, multiple uh, teeth or multiple points coming in contact with the material. Drilling, I think you're pretty familiar with. Milling is essentially drilling. So drilling is up and down, and that's it. Milling is up and down and side to side. You know, notice just here in this picture that you can see that this tool is a lot more robust than what you'd normally think of as a drill bit. And that's so that it can handle these side loadings so that you can move in all directions, really. Not just 3 axis, it can be up to 5 axis. Page and this page is kind of a summary list of the processes here that will be used. I would like to point out one thing, and that is, let's see, notice this contour turning here. I like to compare this contour turning and this form turning. Okay, you end up with kind of the same thing, and I think I want to compare these two just so you can see what these are all about. First off, you know, drilling we talked about, just in and out. Boring is kind of inside turning, and you can do this, you know, with a taper. You can either do a fancy way to put threads on, internal or external. Um, turning, facing, these are a lot of different names for things. Let me focus here on contour turning versus the form turning, okay? So when we talk about contour turning, got my little bit here. So contour turning is just when you're spinning your workpiece there on this is the workpiece. You're just spinning your workpiece on your lathe, and then you move the bit uh, around, in and out, back and forth, and after a while, you end up with a shape that you are trying to get. Right? That's contour turning. That's very familiar. Forming is a little bit different, though. Forming is you have a tool that is essentially in the final shape of the contour that you're trying to make, right? And then so you just gradually bring it in, bring it in, bring it in, and you would kind of scrape it down or form it in one kind of in and out motion to the final uh, to the to the final shape. Okay, and so as you can see here, that's what this is trying to say here with this forming. Is that the forming tool is in the final shape, whereas contour turning, you're just going back and forth and in and out, kind of the standard that you would expect, or that you've come to know with regard to the lathe work. Okay. When we talk about the parameters that are important to us, that's going to be the speed, the depth of cut, and then the feed rate. Let me describe these. Okay, the speed is not the rotation. Okay, speed or velocity, you could say, is in the units of length per time. Okay, rotation is not. Rotation is in the units of revolutions per time, right? Often RPM, what have you. Rotation and speed is not the same thing. Okay, speed. Okay, it's a linear speed. So imagine that you are a little ant standing right here. All you know is that you've got some material that is coming down, straight down, really fast, and striking the tool. Okay, being an ant, you don't really get to see the whole curvature of the tool in this that it is in fact rotating, because you're just standing right there on the tool. Okay, if you can think of it that way, that's what we mean when we talk about the speed. Okay, it's not a rotational speed, but it's how fast is the material striking the tool. Okay, the depth of cut is this right there, as you could imagine, and then the feed rate is how fast the tool is moved down the, in this case, moved down the shaft. I think that's something that you're familiar with. Okay, so it's how fast do you want the material to hit the tool, how deep do you want the material to hit the tool, and then how fast do you want to move the tool down the axis. Okay, and so we've got some examples here that work out, and then on your quiz you've got a couple too that you'll be working out mathematically. Okay, and so these are pretty straightforward. Okay, here's this first question. If you're thinning down a shaft from 2 inches diameter, we're going to be careful about that, 2 inches diameter to 1.3 inches diameter on a lathe, how many passes will this require if you cannot exceed a 0.15 inch depth of cut for each pass? Okay, so we need to be clear here. So this D1, this is our 2 inches, and our final diameter, this is our 1.3 inches. What that means is that this depth of cut is not D1 minus D2, right? Because there's a depth of cut over here, and then there's another depth of cut over on this side because the tool is spinning, okay? So therefore, let's see, we're 2 inches to 1.3. That means we're going to have a 0.7, oops, it means we're going to have a 0.7 inch reduction in the diameter. Okay. Now that's not what the tool has to do. The tool only has to do half that, right? 0.35 inches. Okay, the tool only has to do half that, 0.35 inches, because the tool is going to take off 0.35 inches here, and then the workpiece just rotates, and so it's going to take off this 0.35 inches, this 0.35 inches, this 0.35 inches, and what you're going to end up with then is a 1.3 inch diameter shaft at the end of that. Okay, so there's a right way and there's a wrong way to do this. As we can see here, 0.35 inches, if 0.15 is all we can do, then we would say, well, if we say 0.35 divided by 0.15 inches, that gives us 2.333, okay? This is the wrong answer, okay? 2.33 passes is not something that we would ever want to do, right? Does a barber ever give 2.33 haircuts? No, okay? And so we're always going to want to round up. So we would say, well, it would take for sure 3 passes, Okay, but look at this. It cannot exceed 0.15 inches depth of cut. Okay, so what we would do then probably is we would do the first pass would be 0.15 inches. The second pass would also be 0.15 inches. And then the third pass, would be whatever's left over, which is the 0.05. A 0.05 inches, right? That's probably what would happen. So the answer here is 3 passes, and you could either solve for this 2.333 and just round up, or just look at this number and say, okay, how are we going to do that if we can't go bigger than 0.15 inches? Okay. Now take a look at this. We've got the same shaft now, 2 inches original diameter. It's rotating at 240 RPM. What is the cutting speed in feet per minute? Okay. This is also sometimes written as SFPM, which would be surface feet per minute. You could also think of that as straight as opposed to curved, right? And so the way we would do that, we would calculate this cutting speed. We would use this equation. Okay, the cutting speed then is going to be the rotational speed here times essentially the circumference. Okay, or in other words, our rotational speed times pi times, we'll say d1 times d1. Okay, and so that's going to be our 240 RPMs, and then pi, well, very sensitive to touching on the screen apparently, times d here, this is 2 inches. Okay, now we'll want to be a little bit careful here when we calculate what these what the units are, right? So um, this is rotations per minute. Okay, and this is kind of the um, surface distance per rotation. All right, is surface distance per minute, right? Or the surface uh, feet per minute. Okay, but we don't have feet yet. What we have here is this pi times the 2 inches. Okay, so this is going to give us, let's see, type this in, 240 times pi times 2 is going to be 1507.96. This is going to be inches per minute. Okay, divide that now by 12, which gives us roughly 125 feet per minute. Okay, that's how that works. We want to be careful when we're talking about feet per minute and then inches, which is very common for diameters. This is a chart that relates the cutting speed to the cost per piece. Okay, what you find if you look at this graph is that the faster you cut, the machining cost itself goes down and down and down nonstop. Okay, you've got these non-productive costs per piece, that's there's a label or it's a certain amount of material that you're using, and so it doesn't matter how fast you go. There's some things that the cost just kind of stays the same. Okay, but we have here this interesting curve, and this is really where I want to focus your attention in this tool changing cost per piece. Uh, if you go faster than ideal, faster than optimum, your tools are going to wear out much faster. Okay. Now, if you double the speed and the tool wears out twice as fast, then do it. Okay. That's not what I'm talking about. That would be an instance of your machining costs going down and your tool changing cost staying the same. But what people have seen when they do this is that if they double their speed, the they might have to change their tools not twice as often, but 4 times as often. Okay, so sure, they're going faster when they're going, but they have to stop and change the tool, stop and change the tool, stop and change the tool. And so what people have identified over a long time is that there really is an optimum cutting speed, right? There really is an optimum cutting speed for which the tools last the longest, uh, and it's as fast as possible, and you get those savings there. Okay, that has led to tables like this. Okay, this is figure 24. So let me point out some things here. So before we get into the details on how to use this, what we have here, now this is just part of this figure. There's a lot more in your book, right? So this is for all of these, for free machining carbon steels that are wrought, medium carbon, uh, leaded. This can include hot rolled, normalized, annealed, cold drawn, or quenched, and tempered. Okay, so there's all of these. There's all of these different options. Okay, what you end up with is the Brinell harnesses here in this range, 225 to 275, or 275 to 325, and then on down as you go on down the list. Okay, so you've got this uh, that you've got these items here. There's all of these rows, and you've got all of these rows. Okay, do not be tricked into thinking that this row matches that, this row matches that, this row matches that. It's not like that at all. Okay, it is that all of these materials right here fall into this category. Okay, all of these materials will have a Brinell hardness of about this. Okay, if the Brinell hardness is more, then you would come down here and you would use this set of numbers. Okay, so think about it just kind of within the box. What these are here is there's two categories. There's, and maybe I'll just draw it like this. There's the inches, and then there's the millimeters. So the bold is in millimeters. The not bold up at the top of that is going to be in inches. Okay, and that is the depth of cut. That's a familiar term that we've used. I want to be careful though that we have both on this chart. We have both metric and SI, or metric and the US units. Okay, and so I'll show you how this works. So for a given material, you would say, okay, what is, well, you say, what's my hardness? And then you say, what is the depth of cut that I choose? Okay, what's the depth of cut that I choose? Okay, and so you pick your depth of cut, and then you go over and you say, okay, what is the tool material made out of? Is it carbide that is uncoated or coated, or is it high-speed steel? Okay, these are the two different examples, or three that are given here in the book, but you can find these tables for a whole lot of different things. And so you would find this, you'd say, okay, what is my, pick one, right? So this is, let's say, I'm going to do something within this range. I want to do this depth of cut, then my speed and my feed would be right here. So those are the two numbers that are really the most important, the speed and feed. Now watch out. Now look at the units here. This is in feet per minute, okay? That's a linear feet per minute or a surface feet per minute. This is not rotational speed, okay? Not rotational speed, okay? We need to calculate rotational speed given the diameter of the tool and the speed that we're trying to hit, okay? And we've got our feed here. This is, again, this is not in a time, it's not inches per second. This is in inches per revolution, which depends on the rotational speed uh, and is not independent. So we need to, if the question is how fast do you want it to spin, you don't know from looking at this table, you've got to do some math. Okay, how fast do you want to move your tool or your bit up and down the shaft? You don't know from looking at this table, you've got to do a little bit of math, okay? And I'll do an example here in just a moment so you can see. Just a reminder, you've got the kind of the US units up here, then you've got the metric down here. I want to make sure that we can keep that separate. Okay, so let's see here. For a 2-inch diameter, 18-inch long shaft rotating at 240 RPMs, how much time will it take to complete 3 passes if the feed rate is 0.015 inch per revolution? Okay, now we need to be clear. This is inch per revolution. So at some point, we're going to need to multiply this by a revolution per minute in order to end up with something that has to do with time, and that's where we're going to get our time. Okay. So 0.015 inches per revolution. Okay. Let's see. I'll see if I can write big. 0.015 inches per revolution. And we know this is 240 revolutions per minute. Okay. Which gives us 0.015 times 240, 3.6 inches per minute. Okay, so that is a rate, though. That's my feed. That's my feed rate in inches per minute. However, I need to come up with a time rather than a rate. So let's see here. 3 passes, okay, 18 inches long. Okay, so for 1 pass, it's going to be 3. Whoops. Let's see. For 1 pass, it's going to be 18 inches divided by 3.6 inches per minute. What I'm trying to do is end up with a time in just minutes. Okay. Oops, I wonder why it keeps doing that. Right. 18 divided by 3.6 is going to be 5 minutes per pass. So 3 passes, then it's going to be 15 minutes. Okay. For 3 passes, that's the way that process works. Okay. Let me change gears a little bit and talk about some of these other methods. Okay. Uh, what we see here in this picture is there's let's see, drilling, boring, and reaming. Okay, those are the 4 things that are mentioned here, and so I'd like to review these. So you want to make a big hole, or do you want to make a smooth hole? Do you want to make a precise hole? Right? If you just need a hole in a piece of plywood, just go out and drill it. Okay. If the hole has to be in a very precise place, you're going to want to start with a center drill. If any of you have ever used a drill bit in a drill press, you'll notice that as soon as you turn this thing on, man, that tip starts shaking, starts vibrating, and you're really not going to be exactly sure where it's going to hit the material. And wherever it hits the material, it's just going to go in and keep on going. And so you're going to be off probably by just a little bit. And so if you start off with a center drill, you will not see that wobble at all. And so when you move this center drill up and down, you'll kind of, put a little notch right there in your material at first, and then that's going to help as a guide for the drill, the normal drill that's going to follow. Okay, so once you kind of give yourself a guide using a center drill, then you would drill it. Okay. Now, if you've got a big enough hole and you need it to be true, true just means that the hole is straight and not off at an angle or necking down. Then you could do some truing by boring. I don't usually, I mean, I don't do truing because my stuff is usually, less than 2 millimeters in diameter. But so the final step, and that is if you want it to be nice and beautiful on the inside, this finishing, and you get it with a really, really precise final diameter, you would use a reamer. I assume that most of you have heard of drills before, but let me talk a little bit about a reamer and how that's different. Right, drill bit, this is standard where you got the flutes here, you got the tip. Same thing with the reamer, you got these cutting surfaces, but look at the tip. Look at the tip. Okay, this is not sharp. Okay, whereas a drill here is really made to make holes. It is going to plunge in and it's going to carve its own way. A reamer is not for that purpose. Okay, if you look very closely at the reamer, you'll see that really, and let me see, I'm going to try to maybe draw this right here. The reamer only has uh, the capability of cutting on like its outside, you know, 0.5 millimeters maybe. Okay, this is very, very thin cutting surface. And so the purpose of this reamer is it's the last step. It's kind of a smoothing, kind of a polishing, very nice shaving cut. Okay, and so you'll have a hole pre-drilled with a drill or a punch or whatever, and then you'll come back with a reamer and you'll very carefully, very precisely smooth the hole that you've made with the drill and get the diameter just right. Okay, that's a reamer. Let me talk now about the amount of power that it takes. There's some terms that you'll see here that are new. What we're interested is this primarily is this MRR. That's the material removal rate. Okay, the material removal rate. There's a straightforward way, right? X times Y times Z. You've got the depth of cut, you've got the feed rate, and you've got the cutting speed. Multiply those together, and that's the volume of material per time that will be removed. Okay. This down here, this is the equation that we'll often use when we're talking about the power required. Okay. So there's the power that you have. This is the HP, the power of the motor that's provided. Okay. And you've got the power that it takes to cut. Now, this is a specific energy or a specific power, unit power, okay, in the sense that, look up here, these are the units right here. So this is essentially, um, if it has a unit power of 1, then that would mean a 1 horsepower motor in 1 minute could remove 1 cubic inch of material, okay? So as this number uh, goes up, then that means it takes either more horsepower to remove 1 cubic inch, uh, or it takes more time to remove 1 cubic inch, or with that same horsepower and time, you're going to remove less. Okay, so bigger numbers here mean uh, harder materials, it requires more energy. This is the material removal rate that I talked about just briefly. This is a correction factor, which largely has to do with the age of the tool, right? If the bit is old, if the tool is old, then your correction factor can be more than one, and that just has to do with you know kind of inefficiencies of the drill bit itself. Now this E here in the denominator, that is a mechanical efficiency, largely when we're talking about the motor itself. You've seen mechanical efficiency before. I think early on in thermo, that might have been the first place that you saw it. Um, Let me work out an example here so that I can kind of show you how to do this. Okay, so we've got here a scenario where I've got a Craftsman lathe, quarter horsepower motor. I do have a reduced mechanical efficiency, 80%, and what I've got is a 2-foot long shaft and low alloy cast steel. We'll look at that here on the table in just a sec. 2-foot long shaft, and I'm going to thin this from 2 inches in diameter to 1.25 inches diameter. Okay. Now, if I had a really nice machine, I just go look at the tables and say, okay, well, what do I want to cut this at? What's my depth of cut going to be? What's my feed rate? And I would just do all of those things. However, my machine's too weak, and so I can't do it as much as I'd like. And so my question is, if I'm limited by the horsepower of my lathe, that's kind of what I'm insinuating here. If I'm limited by the horsepower of my lathe, how long is this process going to take? Okay, so let's see here. I'll pull up this equation that we just had. Okay, horsepower. That's the horsepower of the motor. Okay, and this is the specific horsepower, the unit horsepower that's related to the material itself. Okay, we have a material removal rate, this correction factor, and then the efficiency. Okay, I'm just not going to use a correction factor. We'll say we've got a nice sharp tool, and then that's going to be fine. Okay, the horsepower of the motor we do know, that's 0.25. I'm going to be careful with my units here, HP. Okay, and then looking back here, let's see, what did I say? Low alloy cast steel. Low alloy cast steel. This is going to be 0.67. And look at these units, horsepower minutes. Now your book's got a mistake here. It's not horsepower minute inch cubed, it's horsepower minute per inch cubed. And that's what that slash in red there indicates, 0.67. Okay, so this is 0.67 horsepower minute per inch cubed. Okay, we've got an MRR. We don't know that yet. And we've got our efficiency here of 0.8. Okay, now everything's known. Everything's known here except for our material removal rate, so we can solve for that. And that is about 0.3 inches cubed per minute. Okay, so that's as fast as we can remove material. And so my question is, well, how much material am I going to want to remove? Okay, and we would simply say pi d1 squared over 4 minus pi d2 squared over 4. Okay, so that is the area of the two shafts, the starting shaft and the finishing shaft. Okay, and then we'd multiply that now by the length. Let's see here. Now the length is in feet. I want to be a little bit careful here. The length is in feet. I've got inches cubed here. This is going to be in inches, so I'm going to go and put this into inches. So this would be 24 inches. Okay, and that's going to give me the total volume of material that I'm going to need to remove, which is a total of about 46 inches cubed of materials. Okay, so if this is my removal, if this is my material removal rate, about 0.3 inches cubed per minute, and I've got 46 inches cubed, then this is going to take me approximately 150 minutes, or about 2.5 hours to perform this process, right, with this quarter horsepower motor. 2.5 hours, that's a long time. Maybe upgrade that, your next birthday. This table 24 1, gives us some suggested feeds and speeds as a function of what it is that we're using it on. There's face mills, slab mills, end mills. Okay, these are similar to drill processes, but these are the ones that can go up and down and back and forth. Okay, so what we're interested in here, as before, is how fast can we go, and how much or how fast do we spin the tool, and also how fast can we move the tool back and forth through the material. Okay, uh, this is now per tooth. Notice this. Okay, we're now talking multiple points, multiple teeth. So we've got a feed per tooth. Okay, per tooth. Now I've got these colors. Don't think, again, malleable iron and soft hard, cast steel and soft hard. No, it is not that. There is malleable iron that's either soft or hard. Okay, uh, the feed information is here. The speed information is here. Okay, you've got cast steel, which is either soft or hard. Its feed information is here. Its speed information is here. And you just want to go out to whichever column you're interested in: face mills, slab mills, end mills, what have you, and then get that information. Both a range per tooth for the feed, and a range for the speed. Typically what you'll do is just pick a number somewhere within that range, and then try it. And if you can speed up a little bit more, that's okay. Or if you get some chatter and you need to adjust those parameters, that's okay. But anywhere within this range is a good starting point. And so again, we still have this question of, well, how do you go from feet per minute, which is a surface feet per minute or linear feet per minute, to a rotational speed? Here's another here's another equation that we can use for that. Remember before we kind of did that, and I said, oh, well, we've got to watch out, feet versus inches. Um, that can be dangerous. And so this equation, you're welcome to use this if you like, relates the rotational speed with the cutting speed, but now we don't need to worry about units. Okay, we just plug in numbers, and then this 12 right here actually makes this correction for us. Okay, and so we just put in the numbers. So this is going to be the diameter here is going to be in inches. Um, the cutting speed speed is in here, right? Speed is in feet per minute. And then just put in the numbers, and then we're going to end up with this. So our rotational speed we get using this formula, and then also our feed rate, our machine feed rate, and our tooth or per tooth feed rate are the same, because now we've got multiple teeth. And so this equation to get our machine feed rate, or our table feed rate, is our tool feed rate, or our per tooth feed rate, whatever we get from up here, right? Whatever we get from up here, multiplied by our rotational speed, multiplied by actually the number of teeth that are there, because one revolution, now you're coming in contact with one or two or four or six different teeth. Okay. Let me change gears a little bit and talk to you about broaching. Broaching is cool. I don't care who you are. Okay. You can't ever, with a drill bit, your holes are always going to be round. Okay. With a tool, with an end mill, you're always going to have this round hole or circular sidewalls when you get done. Broaching is not that way. Okay. So broaching, you'll see, it's kind of like sawing. Um, yeah, let me flip forward and show you this. So check this out. So these are a couple examples of broaches. Now again, like reamers, I want you to remember that there's no sharp tip on these broaches, that you've got to have a pre-existing hole there, and that hole should be, in this case, at least this diameter right here, or at least this diameter. Okay. And so once you have that hole, you can either push or pull this broach through. And what you notice here, that there's a lot of teeth, and the teeth actually spread out in this direction as you go. And so just as with a saw, that every time the tooth hits it, each tooth takes off of a little bit more material. It's the same way with a broach, is that as you pull it, each tooth is going to take off a little bit of extra material. Okay, here's a little video that kind of talks about that, so you can see it kind of in action. So it grabs it, and then you just pull it through one pass, and then and there you go. Then you're able to cut it all at once. So there's all kinds of different shapes you can produce with broaches. There's no other way. If you need to make a square hole, you cannot do it with a drill bit. I don't care how good you are. Okay, much less. I mean, check this out. Stars and keyways and all kinds of things you can do with a broach, and all you need is a hole that this end can fit in. Let's see. All you need is a hole that end can fit in. Push it through, pull it through, pound it through, and what you end up with is the uh, the the final shape. So these are cool approaches. Okay, so let's talk a little bit about abrasive machining. Okay, what makes this different from other processes is that it has a much higher cutting speed typically, and a shallow depth of penetration. When you think about a drill or a mill or a lathe, you know your cutting speed, and also you say, okay, my depth of cut is going to be just this little tiny bit. Okay, with abrasive machining, your cutting speeds are way up, and you're not really sure how much this particular tiny piece of material impacted the 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 material. Okay, and so you do have variability here. Cutting speed and shallow depth penetration, that's kind of what defines this abrasive machining. Okay, the abrasive particles can be uh, free, just in some kind of a slurry, or floating around. They can be mounted on a resin or belt. That would be, a belt sander, or a paper sandpaper, right? Would be that, where you've got this kind of 2D, where the abrasive is just mounted there, or you can have it kind of as a 3D, three-dimensional abrasive, such as a grinding stone. Okay, and so you kind of got 1D, 2D, and 3D here as far as the constructs. The material that you use, the abrasive material itself, can come in all kinds of different toughnesses and sizes. Here you can see just from this photo, there's some examples. There's actually one feature that is very important, and I'll just spell this here, frangible. Okay, that it's got to be frangible or frangibility. Frangibility. So this is a characteristic of materials that really say whether or not it's suited as an abrasive um, material or as these abrasive pieces. What frangible means is that um, if you grind on it or rub on it, or if you can get it to fracture, it fractures sharp. It fractures sharp. Okay. Um, so if you take a piece of chalk, for example, and you just rub it on the sidewalk, you end up with a nice rounded piece of chalk. Okay, and so that's not frangible. This is not what you want. You don't want your sandpaper to become nice and smooth. Okay, you don't want your grinding stone to just become a piece of polished marble. Okay, you need for it to stay sharp uh, on the very, very small scale. And so you look for materials that are frangible. The size is also important. Here, I'll come down here to this slide first to show you. If you've used sandpapers or other abrasives before, you might have noticed that the grain size, the bigger the number, actually the finer the the particles, the smaller the grains themselves. And the reason why is just kind of a historical thing, and that is that the abrasive particles were originally sifted out or separated out by use of screens, right? So if you've got eight, or so if you've got a screen that has openings on the order of 8 openings per inch, then that would be, so anything that could fit through there, just barely fit through, would be considered a grit of 8. Okay, so if you have more openings, that means the gaps are going to be smaller that the grit can come through, so that the grit that comes through will be smaller. That would be either grain size or grit size or screen size of, in this case, 24. And so it goes up and up and up. As you know, the higher the number, the smoother, or the finer the particles, and the smoother your final finish can be, your surface finish. Uh, if any of you have ever made a pinewood derby or done anything like that where you've had to sand something down smooth, then I think you've had a personal experience with this graph right here. So this surface finish, you're going to be looking kind of over in this direction. For the material removal rate, you want to kind of look over here. Okay, what it says is that as the grit size decreases, then your final surface finish gets uh, better and better and better, right? Um, so you want this number to be small, okay? The smaller that number, the smaller the imperfection on the surface, okay? So the fact that this goes down is a good thing, okay? However, your material removal rate, or in other words, how fast you're able to to perform this process, goes up, then it goes down. Okay, and so in fact, if any of you ever tried to just grab a piece of really, really fine sandpaper and get to work on something, man, you'll be there forever. You'll be there forever, just because it takes so long to apply that surface finish. So better, and what in manufacturing they do in general, and that is that they will start out with kind of this rough abrasive stuff, do something that is fast at removing material, okay, and then once that is achieved, once this particular surface finish is achieved, then you can try for other um, other more polished surface finishes. Okay. Now, This is just a cool example. Water jet, I think many of you may be familiar with that. This is an example of a free abrasive, right? These abrasive particles are just included usually in a canister off to the side, and they're sucked out into the water stream, and then so they come out and you're able to cut very precisely. Um, Here's just a chart that is, I think, kind of cool, and it talks about the thicknesses that you can cut of different materials and the times that it takes. You know, and this goes from aluminum down to, in this case, plexiglass and rubber. Kevlar's on here, which is kind of interesting, and glass and other things that you uh, aren't too familiar with, you know, as far as uh, probably being able to cut with the water jet. And just notice here, you know, okay, so if you've got 0.13 inch thick aluminum, here's kind of how you want to cut it. Okay, if it's 0.22 inches, here's kind of how you're going to want to cut it. But this goes up to 4 inches. So you can cut 4 inches of aluminum with an abrasive water jet. You can cut over 7 inches of steel with a water jet. And that was kind of what I wanted to show you here for with this table, is that, man, you can cut some thick material. Um, and so this abrasive processing can be a really powerful thing. Well, thank you very much. I hope you've maybe by now finished the quiz and got a 100 on it. If not, good luck on the quiz, and we will talk later. Thank you.